Hey everyone, this is Joel at Hamina Wireless. In this two-part video series, we're going to talk about the basics of Wi-Fi. We're going to start with the sort of core building block things that you need to know if you're doing Wi-Fi system administration or design or troubleshooting, or even if you're just curious about Wi-Fi. This two-part series is intended to start with the absolute basics to give you a foundation to build on. So let's take a look at the agenda really quickly. So we'll start by talking about the IEEE and the Wi-Fi Alliance, and the point of that being to kind of show you where Wi-Fi comes from, where the protocol comes from, where the branding comes from, and how the IEEE and the Wi-Fi Alliance work together to make Wi-Fi happen. Then we'll look at the 2.4, 5, and 6 gigahertz bands. We'll talk about their differences. And then we'll take a look at the major 802.11 amendments, sort of the history of Wi-Fi, which is really important since the protocol that we use today is based on the original 802.11 protocol that came out in 1997. And it's all built on that, so it's really important to understand where it comes from. We'll talk about the exact layout of channels in the 2.4 gigahertz band, and then we'll talk about the different types of interference, like co-channel interference, some people call it co-channel contention, and adjacent channel interference. Then we'll talk about channel reuse, how to effectively reuse channels on a wireless network with multiple access points. And then we'll finish up by talking about channel bonding before we wrap up the first part of this video series. So let's jump right in. So the first thing I want to talk about is basically where Wi-Fi comes from. There's two organizations that sort of make Wi-Fi happen. The IEEE, which is the Institute of Electrical and Electronics Engineers, and the Wi-Fi Alliance. Now, I have to put the Institute of Electrical and Electronics Engineers on the slide, otherwise I can't remember what the IEEE stands for. The IEEE makes standards. They create standards. There's a bunch of different standards that they have made that you probably interact with every day. For example, 802.15.1, that is the underlying technical specification for Bluetooth. Now, there's another organization called the Bluetooth SIG, or the Special Interest Group, that applies branding and things like that to Bluetooth, but the Bluetooth as we know it is based on 802.15.1. Another example is 802.15.4, 802.15.4. This drives Zigbee, which maybe you've used for like home automation setups like Philips Hue. Also, I think Thread is based on 802.15.4 and maybe Z-Wave. I'm not sure about Z-Wave, but it might be also 802.15.4 based. Another kind of classic example is IEEE 1394. So you might remember back in the day when the original iMac G3 came out. It didn't have a parallel port. It didn't have a serial port. Instead, it had USB and FireWire. And the original iPod used FireWire. FireWire is based on IEEE 1394. You might remember back in Windows XP, I think the device manager would say IEEE 1394 if you had a FireWire card installed in your PC. Now, another one is, there's a mistake on the slide, I apologize for that, is 802.3. That's the underlying specification for Ethernet networks. And then finally, 802.11, which is the underlying specification for Wi-Fi. So the IEEE makes the standards and maintains the standards, whereas the Wi-Fi Alliance does a bunch of different things around sort of applying branding and interoperability to Wi-Fi. So the Wi-Fi Alliance is composed of a group of major players in the space. Think like Apple, Cisco, Nokia, Ruckus, Microsoft, Dell, T-Mobile, or a couple of other ones that come to mind. Basically, the Wi-Fi Alliance is anybody that has anything to do with wireless or wants to have input into Wi-Fi is involved in the Wi-Fi Alliance. The Wi-Fi Alliance also provides branding for Wi-Fi. They are where the term Wi-Fi came from. They invented that to apply some branding. 802.11 just wasn't memorable enough. It wasn't going to get into people's consciousness, whereas Wi-Fi has proven to get into everybody's consciousness. Everybody knows, they at least recognize the term Wi-Fi. They might struggle to explain exactly what it is, what that means, but everybody knows at least of Wi-Fi. And by the way, it doesn't stand for wireless fidelity. It means nothing. It just sounds cool. That's the whole point of it, was to sound good and kind of catch people's attention, which it totally did. So yeah, Wi-Fi is branding provided by the Wi-Fi Alliance. Some other examples being WPA, WPA2, WPA3. These are basically brand names applied to basically levels of security in the world of Wi-Fi. So the security stuff in Wi-Fi as we know it today, well, partially as we know it today, there's been a lot of changes, comes from 802.11i, which is an amendment to the standard, and then 802.11i was used to create WPA and WPA2. WPA3, I'm actually not sure about off the top of my head. Another example is wireless multimedia. That one was in I think the late 2000s or so is when we saw wireless multimedia hit the scene. But again, based on the IEEE's standards with some nice branding applied to it. Now, the final thing that the Wi-Fi Alliance does, and this is maybe the most important thing that they do, is they ensure interoperability between vendors. Now back in 1997 or so, 1998, when Wi-Fi was in its infancy, before it was even called Wi-Fi, there was actually a ton of concern and criticism that, well, you're never going to be able to get, a wireless network adapter from one company to talk to another company's wireless network adapter. They're not going to interoperate at all. That was a huge point of concern. And there was definitely a point where a bunch of the Wi-Fi Alliance people were gathered in one room and they had to connect a bunch of devices all to each other and see if it would all work. And the press was there and it worked. It totally worked and proved like, yeah, we can absolutely do this. It was a big deal back then and it's still a big deal now. The Wi-Fi Alliance certifies devices for interoperability. If you see a Wi-Fi logo on the box for a smartphone or a smart device or something like that, that means that the Wi-Fi Alliance has certified it to be interoperable with other Wi-Fi devices. So the IEEE makes the standards, the Wi-Fi Alliance ensures interoperability, and applies branding to the whole thing. Cool. So now I want to talk about the differences between the 2.4 and the 5 gigahertz band. Now you might notice that the 6 gigahertz band is sort of absent from this slide. Don't worry, we're going to cover it. In many ways, it's very similar to the 5 gigahertz band. They're right next to each other in the spectrum, as I should be able to show you later on, but we'll just talk about 2.4 and 5 gigahertz for now. So 2.4 gigahertz is in a lower frequency slice of spectrum. And so it because it's in a lower frequency slice of spectrum, it has a longer wavelength. The wavelength is actually physically longer. By the way, these two, the 2.4 and 5 gigahertz examples I have here are not to scale, just to illustrate a longer wave versus a shorter wave. Now, because it has a longer wavelength, it typically has more range. I apologize for the imperial units here, but we typically say that 2.4 gigahertz Wi-Fi has a range of about 300 feet. It's something like 300 feet. Whereas the 5 gigahertz band has a much shorter wavelength since it's a higher frequency, and because of that, it has less range. We typically say something like 90 feet instead of 300 feet, so typically a lot less range. Now, that's going to depend wildly on your transmit power and your access points and your clients and indoors or outdoors and concrete or, is it concrete or wood construction? There's all kinds of things that will change those numbers, but these are kind of the typically accepted numbers for the sort of range that you're going to see. Now, the 2.4 gigahertz band has kind of been around longer. We've been using it for Wi-Fi for a much longer time. This is where Wi-Fi started out back in 1997, was in the 2.4 gigahertz band, and because of that, it's more crowded. There are more Wi-Fi devices operating in the 2.4 gigahertz band, whereas the 5 gigahertz band and to a greater extent the 6 gigahertz band are way, way less crowded. There's also more non-Wi-Fi interference in 2.4 gigahertz. The 2.4 gigahertz band is what we call unlicensed spectrum. Same with the 5 gigahertz band now, by the way, but the 2.4 gigahertz band was sort of the original slice of unlicensed spectrum, which means you didn't have to get a license to operate radio equipment in that band. Because of that, that's where Wi-Fi and Bluetooth and Zigbee and cordless phones and microwave ovens and baby monitors and analog wireless security cameras and all kinds of things operate in the 2.4 gigahertz band that are not Wi-Fi. And Wi-Fi has to compete with those things to talk. And so the 2.4 gigahertz band is just a lot busier when it comes to non-Wi-Fi interference. 5 gigahertz, there is stuff there. You see like analog first-person view drone cameras live there. There's some point-to-point link gear. There's a few things that exist in the 5 gigahertz band, but there's just not nearly as much to worry about there. So we typically don't have to worry about interference in the 5 gigahertz band. So when you look on the box to buy a Wi-Fi device, whether it's an access point or a wireless network interface card, a client device, whatever, you're going to see that it supports some flavor of 802.11. if you see that it supports 802.11b, G, N, and AX, and you could drop any one of those sets of letters from it and it would kind of work the same here, that means that it's probably a 2.4 gigahertz only device. It probably only operates in the 2.4 gigahertz band. Whereas if you see 802.11a or 802.11ac on the box, that means that it supports the 5 gigahertz band. Those are amendments to the standard that only exist in the 5 gigahertz band. So that's a dead giveaway that it has 5 gigahertz support. Just watch out. If you go to the store right now in 2025 today and you buy, let's say you get like an 802.11ax router, that does not guarantee 5 gigahertz support. That doesn't guarantee 6 gigahertz support. That could be a 2.4 gigahertz only device. So watch out for that when you are shopping for access points and client devices. All right, let's talk about sort of where Wi-Fi came from. And I just kind of want to march to the history of Wi-Fi and kind of talk about the different things that came along with the different amendments over the years. So 802.11 was the original standard. This standard came out in 1997. It was in the 2.4 gigahertz band, and it had two data rates, 1 megabit per second and 2 megabits per second. And to get those data rates, it used a modulation technique, a way of putting ones and zeros on the air called DSSS, or direct sequence spread spectrum. Don't worry about what the acronym means. I just want you to see the pattern here. So you don't need to remember that DSSS stands for direct sequence spread spectrum. It really doesn't matter. I just want you to see the pattern. DSSS had a channel width of 22 megahertz. So it's 22 megahertz wide was the width of the channel in the spectrum. So then by 1999, we'd had 10 megabit Ethernet for a long time. 2 megabits per second was pretty pokey even by 1997 standards. And so the IEEE introduced the first amendment to the standard called 802.11b. 802.11b, like I said, came out in 99. It was still in the 2.4 gigahertz band, and it added two new data rates, 5.5 and 11 megabits per second. And they used a slightly fancier modulation scheme, a slightly more complex way of putting the ones and zeros on the air, and they called it HRDSSS, or high rate direct sequence spread spectrum, and it supported it had a channel width of 22 megahertz. But the thing I want you to notice here is high rate direct sequence spread spectrum is backwards compatible with direct sequence spread spectrum. You see the lineage happening here. All right, so 1999, it's basically for all intents and purposes on the same piece of paper. The IEEE also introduced 802.11a. 802.11a, instead of being in the 2.4 gigahertz band, worked in the 5 gigahertz band. So kind of a brand new slice of spectrum. And they introduced a brand new modulation scheme that could hit 54 megabits per second, which was really good because fast Ethernet, 100 megabit Ethernet, was on the horizon. And so they really need to start thinking about speed a little bit, making things a little bit faster. So the new modulation scheme, OFDM, stands for Orthogonal Frequency Division Multiplexing. Again, don't worry about the acronym, what it means. It doesn't matter at all. OFDM is used in tons of technologies all over the place. It's used, I think, quite a bit in cellular technologies. It's used in like DSL, for example. There's probably hundreds of examples out there. It's a very common modulation scheme, but it was the hot new thing for 802.11 back in 1999. Now the channel width went from 22 megahertz to a slightly narrower 20 megahertz. So we went just a little bit narrower on the channel width. Now, remember earlier, 802.11b, backwards compatible with 802.11 prime. 802.11a, on the other hand, was in a brand new slice of spectrum, and so it wasn't backwards compatible with 802.11b and thus 802.11 prime. Now remember we talked about the range issues earlier, how 2.4 gigahertz had a range of about 300 feet or so, whereas the 5 gigahertz band was limited to about 90 feet. That absolutely applied here. So businesses and consumers kind of had to make a decision. Really, I would say mostly businesses at this point. I don't think 802.11 had any penetration into the home markets yet. But they kind of had to make a decision between range versus speed. And I think for most applications, speed ended up winning. Not speed. I said that completely backwards. Rate ended up winning. And so I said it wrong twice. It wasn't speed that won. It wasn't rate that won. It was range that won. Range was the thing that people were looking for, and so 802.11b ended up being a lot more popular, even though 802.11a was faster. Whew, I'm glad I caught that. That would have been annoying to try to fix in editing later on. All right, so then fast forwarding to 2003. We have this problem where we have one standard with bad range but good speed, and another that has good speed but bad range. What do we do? Well, what the IEEE decided to do was to introduce 802.11g. 802.11g came out in 2003, and that's definitely when, I don't know if you can see it, that's definitely when this guy became very, very popular. This is from maybe 2004, 2005, but the Linksys WRT54G, oh, this is from 2007. This is a later model, but this was absolutely foundational to, making Wi-Fi ubiquitous, making Wi-Fi absolutely everywhere. The WRT54G was a consumer 802.11g Wi-Fi router. This is the first wireless router that I ever touched, actually. Maybe not the first. I think I had a D-Link before that, now that I think about it. Anyway, what 802.11g did is it took that swanky, fancy modulation scheme, OFDM, and it brought OFDM down to the 2.4 gigahertz band. It's still orthogonal frequency division multiplexing. They called it ERP, Extended Rate Physical OFDM, and it gave us 54 megabits per second in the 2.4 gigahertz band with that 20 megahertz channel width. And it was backwards compatible with 802.11b and 802.11 prime. Basically the best of both worlds. And it really allowed consumer grade Wi-Fi, and I think Wi-Fi in businesses and things like that, it really gave them the opportunity to take off. Cool. So now, fast forwarding a little bit to what I consider to be the modern era of Wi-Fi. This is kind of where I draw the line, and I say that anything below this like pink line is kind of what I call modern Wi-Fi. We got 802.11n. 802.11n was a brand new kind of unifying standard or unifying amendment to the standard. It worked in both the 2.4 and the 5 gigahertz bands. It gave us another channel width to work with. So originally we just had 20 megahertz, so just one 20 megahertz wide channel. It also gave us a 40 megahertz wide channel. So double the channel width means basically a wider road to put more throughput through, so we could hit faster speeds with it. Now all the vendors out there advertised a maximum data rate of about 600 megabits per second or so. We really didn't see that in the real world. The standard outpaced what was possible in the real world in this case, and that's going to be a theme going forward. That's a pretty typical thing that has kept happening in the years since. But this was backwards compatible both with 802.11g in the 2.4 gigahertz band and with 802.11a in the 5 gigahertz band. Now, from a complexity perspective, the 802.11n amendment was a monster of complexity. Things got really complex with 802.11n. I remember Matthew Gast wrote a book called The 802.11n Survival Guide. I think that's what it was called. Brilliant book, but just kind of underscores just how complicated the protocol got. But that's partially because it brought everything under one umbrella. Now, keep in mind, even back then, even still today, you can go out and buy an 802.11n device that only works in 2.4 gigahertz. In some very limited cases, you could buy an 802.11n device that only worked in the 5 gigahertz band. That was possible. But then there were a lot of devices out there that supported both. They would be 802.11n, they would have an 802.11n on board, and they would have both a 2.4 and a 5 gigahertz radio, and they would be able to connect on one band or the other. Great, so then moving along to 2013, we got 802.11ac. So 802.11ac was a 5 gigahertz only standard, which is a little bit disappointing. I think that there was a little bit of a misstep here by ignoring the 2.4 gigahertz band. This one focused on raw throughput. They called the modulation scheme VHT, or very high throughput. And we were promised, like 7 gigabits per second or whatever. Didn't happen. It did bring a lot of speed improvements, though, largely because it gave us even wider channels. So now we got 20, 40, 80, and even 160 megahertz monster wide channels that we could shove tons of data through all at the same time. Okay, moving forward a little bit, we get to 802.11ax in 2021. So I kind of split this apart into two pieces, and you'll see why in just a second. So 802.11ax works in both the 2.4 and the 5 gigahertz bands. Of course, it's backwards compatible with AC, which in some ways is backwards compatible with 802.11n, and of course, it's backwards compatible with 802.11n in the 5 gigahertz band. You can kind of see how this is all going here, and it focused on efficiency inside a coverage cell. We had all the same channel width still, and we thought maybe we could get towards 9,600 megabits per second, maybe getting towards a gigabit per second. But again, we just didn't realize that outside a lab environment. Okay, the big one, the most important one, is 802.11ax. 802.11ax also came out in 2021, but it takes advantage of the brand new 6 gigahertz spectrum. The FCC and a bunch of other regulatory bodies all over the world opened up the 6 gigahertz band for use for Wi-Fi. This was a project that was many years in the making. Tons of the Wi-Fi vendors and people at the vendors worked very hard on this to convince all the people that were already using 6 gigahertz and to convince the FCC that we could do this, we could use it without interfering with things that are already there. And so with 802.11ax, we got 320 megahertz wide channels in addition to all of the channel widths that we already had. This is the biggest development in Wi-Fi since 802.11n. Frankly, I haven't been very excited about 802.11ac and even about 2.4 and 5 gigahertz 802.11ax. I still think you could run a modern wireless network with 802.11n access points, and for most use cases, you would probably be fine. Now, don't get me wrong, the access points would be a huge pain to manage and it wouldn't be cost effective, but you could. 802.11ax is different though. Opening up the 6 gigahertz band gives us a lot more throughput for a lot more spectrum, and that's really exciting to me. Now, one thing you may have noticed is that some of these say like Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, Wi-Fi 6E. What's going on with that? Well, the Wi-Fi Alliance looked at the alphabet soup that was going on here, and they decided to apply some branding. And so they kind of applied these as backronyms. Note that there is no Wi-Fi 3, there's no Wi-Fi 2, but they're sort of implied. And so this makes it easier for the average consumer to look at the box and understand what they're getting. Now, you might be wondering, why, Joel? Why did we just spend, however many minutes on these amendments? Like, why are we focusing on the old stuff? Why didn't we just look at the new things that are happening here and focus on that instead? Good question. The reason for that comes down to the backwards compatibility. Remember, I pointed out earlier how 802.11ax is backwards compatible with AC and backwards compatible with N, which is backwards compatible with G and backwards compatible with B and backwards compatible with 802.11 prime. The IEEE is obsessed with backwards compatibility. So as a result, most of the data that is moved around on your home network in the 2.4 gigahertz band today is using the original 802.11 standard. Most of the beacons, probe requests, probe responses, the actions of devices joining and leaving your home wireless network in the 2.4 gigahertz band are happening at the legacy 802.11 data rates. It's the foundation for the protocol. And this isn't going to change anytime soon. And the same is true in the 5 gigahertz band. If you have 5 gigahertz on your router or whatever you have at home right now, I guarantee you do, it's transmitting stuff at 6 megabits per second as a minimum basic data rate. These are the 802.11 prime and 802.11a serve as the foundation for everything Wi-Fi today. So I think it's absolutely critical to understand where it came from and what all the different amendments did. Thanks for sticking with me through that. Cool. So now let's talk about the different channels. We'll start out by looking at in the 2.4 gigahertz band. Now, in the 2.4 gigahertz band, the channels are marked by their center. That's actually true in 2.4, 5, and 6 gigahertz. We always mark the channel by its center, but the channel width is 20 megahertz wide. That's the actual width of the channel. And if you look at this little chart here, you can see we've got channel 1, channel 6, and channel 11. Those are the 3 channels in the 2.4 gigahertz band that don't overlap. And you might be thinking to yourself, well, hang on just a second, Joel. I've configured a few access points and routers in my day. I'm pretty sure there's more than 3 channels in 2.4 gigahertz. You're right. Here's the problem. The problem is that each channel is marked by its center, and the channel centers are only separated by 5 megahertz. There's only a 5 megahertz gap between the channels, but the channels are each 20 megahertz wide. And so when you do the math really quick, you carry the one, you realize that there's really only enough room in the 2.4 gigahertz channel or the 2.4 gigahertz band for 3 channels that don't overlap. We really only have about 60 megahertz worth of space to work with in the 2.4 gigahertz band. As a result, most of the channels in the 2.4 gigahertz band partially overlap. So the next question you might have is, why does that matter? Well, it matters because of adjacent channel interference. Let's say that you've got an access point that's on channel 5 and another access point on channel 6, and they both have a client associated to them and they're transmitting some data to the client. If they transmit at the same time, they are going to basically destructively talk over each other. Since channel 5 and channel 6 overlap by about 75%, they're going to basically interrupt each other. They're both going to have to back off, wait for another opportunity to talk, try again, maybe interrupt each other's transmissions again. They're going to have a bad time. It's not going to go well. Think of it as kind of like having dinner in a noisy restaurant, and there's a really noisy table right next to you. So you're having a conversation at your table, everybody's taking turns talking really politely, it's going really well, but then there's this table next to you and they're talking really loud too, but they're not part of your conversation. So you're talking and they're talking at the same time, so you have to talk a bit louder to compensate, they have to talk a bit louder to compensate, until pretty soon you're going, what? Sorry, I couldn't understand you, with the people at your own table because of the noisy table next to you. Adjacent channel interference is just like a noisy table next to you at a restaurant. Now, there's another type of interference out there called co-channel interference. It's actually even way more common than adjacent channel interference. Co-channel interference is sort of a standard, normal thing that happens in Wi-Fi that Wi-Fi is built to handle. So, to understand co-channel interference, let's talk about the half-duplex nature of Wi-Fi. Now, with Ethernet has multiple twisted pairs of copper inside the cable, and because of that, we can send traffic in 2 directions on the Ethernet cable at the same time. It's kind of like a 2-lane highway. You can send traffic east and west simultaneously, whereas Wi-Fi is more like a one-way road. We can only send traffic in one direction at a time. So let's take a look at an example. Let's say that we've got a laptop here and we've got an access point, and the laptop needs to transmit some data to the access point. So what it's going to do is it's going to check the air. It's going to listen to see if anything is talking, and if nothing is talking, it's going to transmit its data over to the access point. Then the access point, on receiving the data, will go, yep, check, I understood the data, and it will reply with what's called an acknowledgement, or just an ACK for short. So we send data, we receive an acknowledgement, we send data, we receive an acknowledgement. By the way, the directions of the arrows, you can totally flip these around and point them in the other direction. The access point, if it transmits data to the client will send an acknowledgement as well. Now, there's a couple of things that can go wrong here. Let's say that the access point is kind of far away and the client transmits the data, but it just never really makes it there, and it's just too quiet for the access point to understand. The access point is going to do nothing. It's just going to do nothing. And then the client's going to start wondering, like, okay, I never heard an acknowledgement, so the access point must not have received the data frame. So it will transmit the data again and again and again. It'll keep transmitting that data until it either gives up or finally something makes it through, and the access point can go, yep, check, I understood the data, and it will reply with that acknowledgement. Wi-Fi is a lot like my kids, and if you have kids, probably like your kids too, where if you've ever been sitting on the couch reading a book, or I don't know, maybe you're playing a video game or watching some TV or something like that, your kid might say something to you. They might ask you a question or something like that, and if you don't reply, what is a kid going to do? They're going to repeat the question, and they're going to repeat it again and again and again, and they'll keep repeating themselves until finally something makes it through, and you go, yep, check, I understood that something was just sent to me. And then you'll reply with acknowledgement. And then, of course, since they're a kid, there's going to be like a million more data frames that they have to transmit over to you, right? Wi-Fi is exactly like kids, especially toddlers, in this way. So in this example, we've just been looking at a single client and a single access point. What happens if we have multiple clients all around an access point, or all associated to an access point? So let's say in this case that we've got a phone here and it's actually kind of far away from the access point. So one thing that'll happen is that if a phone transmits some data to an access point, and this is true of any client device, if it transmits some data to an access point and the access point doesn't acknowledge it, the phone will slow down and pick a slower and more reliable data rate. If it uses a fast data rate, then it has to go really fast, and you might not be able to understand what is being said if the room is really loud. You know, like let's say that you are, let's say that you're in a really noisy room and you're having trouble understanding someone, and so they keep talking really fast, and you just can't understand what they're saying, and so you say, "Hey, can you slow down a little bit?" And then when they slow down, they're a little bit easier to understand. It's exactly the same way with Wi-Fi devices. If a phone or any client device is having trouble talking to the access point, having trouble getting acknowledgments back from the access point, you can flip this around the other way, by the way. It doesn't matter which direction this is going in. It might slow down to a legacy data rate, maybe all the way back down to 1 megabit per second. We might slow down to the original 802.11 data rate from 1997. So let's say that we've got this device is transmitting at 1 megabit per second, and then everything else is maintaining 65 megabits per second. They're not having any problems, so 65 megabits per second is no big deal. In this case, this phone is going to take 65 times longer to transmit the same amount of information. On any given channel at any given time, only one device can talk. One device gets to talk on a channel at a time. If this phone is transmitting, everything else on the channel has to shut up and be quiet and wait for its turn to talk. And if it's talking at 1 megabit per second or 65 times slower than all the other devices here, it's going to take a ton of time on the channel. It's just like the slow kid in the back of the classroom. You know who I'm talking about? There's in almost every class you've ever taken, there's always this guy. And every time he sits in the back, and or maybe he sits in the very front, I don't know. But whenever he raises his hand, you're like, oh no, here we go again. You know he's going to take forever to ask his question. And usually his question isn't a question, it's usually a statement to make him look smart. You know who I'm talking about. You have someone in mind that has done this, right? A device that's had to slow down to a very slow data rate like this takes up more time on the channel, just like when somebody raises their hand and starts asking a question very, very slowly. Teach, you know, I was thinking about what you said, and I had a question. And you're like, dude, just spit it out. Just say what you want to say. Get on the air and get off the air. That's exactly what happens in the world of Wi-Fi devices. The more devices you add to a channel, the less opportunities there are for everyone to talk. If devices talk slower, they consume more time. So we want to design our networks to make them talk as quickly as possible so devices get on the air and get off the air as fast as possible. And we do that to reduce co-channel interference. Now, one thing I've done here is I have one access point and a bunch of clients. This applies to multiple access points too. Let's say that we've got a whole bunch of APs that all happen to be on the same channel, and they also have client devices all connected to them. They're all on the same channel. Everything on the channel has to take turns talking. Your network, other people's networks, it doesn't matter. Everything has to share the channel. On any given channel at any given time, one device can talk. And if there's one thing that you take away from this video series, that's the thing that I want you to remember. So, to reduce co-channel interference as much as possible, one thing that we employ in wireless network design is we do effective 2.4 gigahertz channel reuse. We carefully reuse our channels. In this case, I have separated out the channel 1s and the channel 6s and the channel 11s. I've kept them all far away from each other so that they can't hear each other, so that they don't have to take turns talking. If you have multiple access points on your network, you want to carefully reuse your channels to try to reduce or eliminate co-channel interference. Okay, so before we go any further, I want to go take a look at just a couple of things. First off, let's go take a look at the spectrum, the radio spectrum. So I'm actually going to go to my website. This is spectrum.potatofy.com. This is a little tool that I came up with in my spare time to use for illustrations and things like this, and it's free. You can go access it and use it as well. So this is an interactive spectrum chart that kind of looks like a Wi-Fi scanner. If you've ever used a graphical Wi-Fi scanner like Insider or Wi-Fi Explorer, we have one in Hamina OnSite. then it kind of looks like this. But this is meant to just be a static channel chart. So right now I've got Bluetooth enabled. So you can see each one of these spikes is a Bluetooth channel. Let's go ahead and disable Bluetooth. And now we're just looking at the 2.4 gigahertz Wi-Fi, channel 1, channel 6, channel 11. Japan has a weird channel. They've got channel 14, but you can only use 802.11b stuff up there. So DSSS, or direct sequence spread spectrum, makes a curve shape like this in the spectrum, whereas OFDM, orthogonal frequency division multiplexing, again, don't worry about remembering the acronyms, it makes a flat tabletop shape in the spectrum like this. Let's disable Japan to get that one out of the way. So there's our three channels, 1, 6, and 11. Let's turn on our overlapping channels. So you can see there's all the overlapping channels and the big mess that they all create for themselves. We'll turn those back off. Now let's zoom out and go find the 5 gigahertz band. So there's 2.4, zoom way out and pan up here. And now this is the 5 gigahertz band. Each one of these channels is 20 megahertz wide, just like in 2.4, but to fit them all on the screen, you have to zoom out a little bit to make them all fit here. So there are 25 channels for us to work with in the 5 gigahertz band. Now, directly above the 5 gigahertz band is the 6 gigahertz band. Oh, in fact, there are some new channels up here. It's called Uni 4 is the little band that they live in. Let's turn those on really quick. I don't know if very many devices support these, but notice that when we turn the Uni 4 channels on, we actually get almost contiguous spectrum, all the way from 5.0 gigahertz all the way up here to, a little bit up past the 7 gigahertz band. So this spectrum here, let's zoom in on it. This is the 6 gigahertz spectrum here. So 5 and 6 gigahertz sit right next to each other. Look at how much space there is. There's tons of room, not just in the 5 gigahertz band, but also up in the 6 gigahertz band. And remember how we talked about how on any given channel at any given time, only one device can talk. And so having more channels is going to give us more space for more devices to talk and more throughput. Cool. All right, so now that we've looked at the 2.4 and the 5 gigahertz bands, one thing that I also want to check on is I want to look at wider channels. So one thing I'm going to do is I'm going to come up here to this menu and I'm going to turn on 40 megahertz channels. Remember how we talked about 802.11n added 40 megahertz channels. So before we had these 20 megahertz ones, and they serve as building blocks for building out wider channels. In 802.11n, we called that channel bonding. Now we just call it wider channels because there's a bunch of them. So let's turn off the 20 megahertz channels, and now you can see there are all of our 40 megahertz channels. But notice what happens when we go to 40 megahertz channels. We cut the amount of channels that we have available in half. How many devices can talk on a channel at a time? Just one. So while 40 megahertz wide channels give us more speed, more throughput, we still can only have one device talking on that channel at a time. And when we cut the amount of channels that we have available in half, that makes channel reuse a little bit harder. But wait, there's more. Let's go up to 80 megahertz channels. So now these are all of the 80 megahertz channels in the in the 5 and 6 gigahertz bands. It's starting to look not quite as spacious now, is it? Let's go with more. Here are the 160 megahertz wide channels. In fact, if we go back and we look at the 5 gigahertz band only, and this is including the new Uni 4 stuff, we're back to having only 3 channels in the 5 gigahertz band. When you push to these wider channels, in that never-ending pursuit of speed, you're gonna run out of channels to work with. You're not going to be able to effectively reuse your channels. There's one more. We have to look at it. 320 megahertz wide channels in the 6 gigahertz band. This is where the really big numbers come from. When a vendor on the box for their access point says that it supports 7 gigabits per second or whatever, it's because they're using these super wide channels for their examples, and they're just not realistic in the real world. For most enterprise network designs, you're typically going to stick with a 20 or a 40 megahertz wide channel. In some cases in the 6 gigahertz band, you're going to use 80 megahertz wide channels, but mostly it's going to be 20s and 40s. Cool, so let's switch back over to our slides really quick. And remember that we were talking about channel reuse in 2.4 gigahertz, and I had, this little 1, 6, and 11 thing going on. If we go look at just the 5 gigahertz band, you can see that it's really, really easy to reuse channels there. You don't have to balance things quite as much if you're using a 20 megahertz wide channel. In fact, there were so many little circles here, I didn't even bother to give them all different colors like I did in 2.4 because that was just going to be way too much work. I don't think I had to reuse a channel a single time when I made this example of this chart. Okay, so one last thing that I want to do before we kind of get off the topic of channels and channel planning is I want to show you what it looks like in a network planning tool like Hamina. So this is Hamina Network Planner. This is our tool. It's like a web-based Wi-Fi design, site survey, and monitoring tool. And what I've done here is I've got a map with some walls drawn in. Let me put it in 3D so you can see what that looks like. So here we go. Little clinic. All the walls are drawn in, and then we can drop in access points. And let's go switch to 5 gigahertz. It will calculate what the coverage is going to be like based on all the walls and things that you've modeled in the tool. So it's great for making network designs. So what I want to do now is let's switch over to the 2.4 gigahertz band. So there's our coverage in 2.4, and I want to look at interference. So this is going to show us anywhere that our access points are interfering with each other. If it's green, that means that we can only hear one access point on the channel right there. Whereas if it's orange or yellow, that means that we can hear two access points on the channel right there. So if I hover my mouse around here, you see that some of the access points get a little red halo around them. In fact, let's make this a bit bigger so that you can see. There we go. Yeah, so as I hover my mouse, you see that some of these get a little red halo. That means that we can hear both of those access points above a certain threshold, and that means that we're going to be able to hear both of them. And so we'll have to wait we'll have to wait and make sure that neither of those access points are talking before a device that's located under my mouse pointer will be able to transmit because they're on the same channel. So if we look at the 2.4 gigahertz band, because we only have 3 channels to work with, it's hard to find a good channel plan that's going to work. You know, earlier, when I showed you that slide, I had these pretty little circles, and it's all 1, 6, and 11, and it's so nice. No, that's not the real world at all. Coverage cells aren't little circles. They're big blobs like this, and like this, and like this. And they overlap all over the place. No matter how far you turn the power down, you are always going to have co-channel interference in the 2.4 gigahertz band. But one thing that Hamina does is it will automatically turn off some of the radios. Notice that if I click on this one, we don't get any coverage from it in 2.4 because the radio is off. You see here underneath, in fact, let's go bigger, zoom. We'll go to 200%, yeah. So now you see this radio is off, whereas the 5 gigahertz radio is on channel 157. And let's go look and see where that one is. So we'll go to 20 megahertz. We'll zoom in. Channel 157, that's the 20 megahertz channel that it's on. And then we have the 6 gigahertz channel right here. So let's go take a look at those other bands. I'll make it a bit smaller so we can use the UI a little bit better. Cool. So if we go to the 5 gigahertz band and we switch over to interference, we only have a little bit of co-channel interference here. Yeah, not bad. Now let's go look and see which channel width I'm using here. I think I a minute ago saw that it was a 20 megahertz wide. Okay, we're using 40 megahertz wide channels here. So we're using the 40 megahertz channels right now. And if we take some of the channels out of our channel plan, you know, maybe the country that we're in doesn't support these channels. Maybe there's terminal Doppler weather radar there, so we can't use those channels. If we take those out, it'll rerun the channel plan and we'll see that there is more interference. In that case, what we might have to do is back down to a 20 megahertz wide channel. It'll rerun the channel plan again for 20 megahertz, and there we go. Now we have effective reuse and we don't have anything overlapping. Let's go look at 6 gigahertz. Do we have anything here? Yep. We have some co-channel interference in the 6 gigahertz band. Let's go take a look at our channel plan and see what we're using here. We're using 80 megahertz channels. Let's back down to 40s and see if that helps. So back down to a 40. Yeah, we've almost completely eliminated the co-channel interference in the 6 gigahertz band. Great. Oh, and one reason why we had interference in the 6 gigahertz band here at all is because the regulatory domain for this project is in Europe. So this is in Finland. So if we go to our spectrum chart and we look at our 6 gigahertz band, and let's take out, we'll show 20s, 40s, and 80s. Let's take out everything except the EU. Notice that in the European Union, we get less than half of the amount of spectrum that the US does. So the regulatory bodies here have only opened up about 500 megahertz for us to work with, whereas the US has, I think it's like 12 or 1300 megahertz to work with. There's a lot more space for a lot more channels here, and Hamina had automatically accounted for that. Cool. So with that, let's jump back into the slides to kind of finish things up really quickly here. So we talked about the channel bonding stuff outside of the slide deck, but I just kind of wanted to point out a few things from it very quickly. So channel bonding is what we called it back in the 802.11n days. That's when we would take two 20 megahertz wide channels and quote unquote bond them together to give us a 40 megahertz wide channel. A wider channel means higher data rates. Then with 802.11ac, same as before, but now we have more options. We now have the 80 and 160 megahertz wide channels as well. Here's an example of an 80 megahertz wide channel. Here's another 80 megahertz wide channel. You could see the channel number notated here as well. So are they useful? Great question. In the 2.4 gigahertz band, not so much. There just isn't enough bandwidth to bond them together and do anything meaningful. We almost always stick with 20 megahertz wide channels in the 2.4 gigahertz band. In the 5 gigahertz band, my strategy is to use a wide channel until you can't. Start with a 40 megahertz wide channel and keep placing access points until you just don't have the frequency space left anymore, and then switch back down to a 20 megahertz wide channel. In fact, Hamina will do that for you automatically. I uncheck the boxes that let it just automatically pick a channel width. It'll just do it and tell you when it did it. Now, in the 5 gigahertz band, you're basically going to never do an 80 megahertz wide channel in the enterprise. You're almost always going to start with a 40 and then drop down to a 20. In the 6 gigahertz band, it really depends. I've heard a lot of people say, at least in the US, that they're starting with 80s and then backing down to 40s. 80s are the new 40s, but your discretion on that. Take a look at your environment, put it into a predictive model, and see how it looks before you do your deployment. All right, so that about wraps up part 1 of Wi-Fi 101. You might be wondering what's next. Well, first off, watch for Wi-Fi 101 part 2. There will be a second part to this video, and also check out Hamina's training options. We offer a number of certifications. They're taught by a third party, our good friend Peter McKenzie. He is an absolute Wi-Fi design and troubleshooting pro, probably the world premier Wi-Fi packet analysis guy. He is good. He is very good, and he's a great teacher and super engaging to listen to. I can listen to him talk about Wi-Fi stuff for hours. He keeps it very interesting. And he doesn't work for us, so he can say whatever he wants about our tools, which I think is great. The Hamina Certified Network Architect is sort of the multi-day, soup to nuts, everything you need to know about doing Wi-Fi design course. And the great thing about it is when you come out of that course, it's not just a how to use Hamina course. It is a how Wi-Fi works and how to create good network designs course. You could take that information and apply it to any tool that you want, and it'll work. There's a couple more lightweight certifications like the planning specialist and the survey specialist. Check out hamina.com/training for more information. And then finally, there's another certification program out there called CWNP, or Certified Wireless Network Professional. I especially recommend the CWNA, the Certified Wireless Network Architect. Whether you take a boot camp or self-study for that, it is a great certification to get. The CWNA Study Guide by David Coleman and David Westcott practically lives on my desk as my Wi-Fi Bible. I cannot recommend it enough. So that is a great place to be as well. But yeah, watch out for Wi-Fi 101 Part 2, in which we will do more of this stuff. Thank you very much for watching this video. I really appreciate it. If you have any questions, please feel free to post them in the YouTube comments down below. More than happy to answer any questions there. You can also email me at joel@hamina.com. If you have technical support questions or sales questions or anything like that for Hamina stuff, I encourage you to email support@hamina.com. I am in that inbox, as well as several other CWNE level guys at Hamina, just like myself, and we're all over the world. So that's the fastest way to get a hold of us, is at support@hamina.com. Thanks again for being here. I really appreciate it, and I hope to see you soon. Bye now.